8.4 today. I think we can finish 8.4 today. We'll just kind of see how it goes. So a section called Matrix Algebra. Sounds like it's kind of complicated. Most of the stuff in this section is not complicated, but it does give us another tool for solving systems of equations. Again, without a calculator or computer, it seems like this might be more work than just solving by substitution or elimination. But again, a lot of the ideas here are preparatory to working in other areas of science or math. There are lots of places where matrices come up, and if you just kind of are familiar with the basics, when you see them again later on, you're going to be much better able to handle them. So kind of keep that in mind as we go through and do this. Okay, so basically we're going to learn how to add, subtract, multiply, kind of divide matrices, and we're going to learn how to solve a system of equations using matrices. So just a quick reminder, a matrix is a blank of numbers. I should have said numbers here. Array, okay? And what does array stand for, or what does that mean? It's an arrangement, okay? It's a rectangular arrangement of numbers, okay? So the individual numbers are called entries, or the other word we can call them are elements, okay? So you can call it an element of the matrix or an entry in the matrix. So remember, we can denote its position by saying, like, this would be A3, 1. So that would be the matrix A, third row, first column, or something like that. Okay, the dimensions of a matrix are the number of rows, always rows first, by the number of columns, always columns second. Okay? So we did an exercise like this last week where all we had to do was look at something and determine the dimensions. So this is a 2 by 2, 2 rows, 2 columns. What's this? Okay, 2 rows, 1, 2, 3 columns. So this is a 2 by 3, and it's a huge deal knowing what the dimensions are. If you screw that up, a lot of these problems become impossible. The next one, 3 by 3, and the last one?
2 by 2.
Careful, 1, 2, 3 rows. So again, always count the rows and then count the columns. So this is a 3 by 2. Now, the first one and the third one, A and C, those are both square matrices. Square matrices are used quite a bit, but we can still do operations on matrices that are not square matrices. In fact, most of the time that's what we end up using. They probably have the most broad applications, or the ones that you'd see in industry and stuff like that. Okay, so for equality, okay, in order for matrices to be equal, they must have the same dimensions, and I'm just going to write DIM for dimensions. Okay, and be equal, and we'll say element by element, or entry by entry. So if we look at this example 2, part A, we want to know whether these two matrices are equal. Well, this is a 2 by 2, and this is a 2 by 1. Is there any way they could be equal?
No.
It's not possible. If they don't have the same dimensions, we can't even go through and check element by element to make sure that they're equal. So on this one, this is a 2 by 2. This is also a 2 by 2. Could they be equal? They could, because they have the same dimensions. And then how we check is we go through and we check element by element. So we check the first row, first column, 3 here, 3 there. First row, second column, -4 here, -4 here. Second row, first column, 4 and 4. Now, if these are going to be equal, we can then say, well, x would have to be -6. I mean, it's literally that simple. You just go through and look in the corresponding place, element by element, they have to be equal. Okay? Any questions there?
So, wait, B isn't a yes or no question?
It's not really yes. Yet this one is no. There's no way they could be equal. This one's going to be a yes as long as we said x was equal to 6. Okay? All right. Good there? Okay, so let's talk about addition and subtraction. Okay, in order to add and subtract, they have to have the same, take a guess, they have to have the same dimension, and then we just go through literally and just add or subtract, as the case may be, element by element. The dimensions, and here's a new word, the dimensions of the resultant matrix, or the result of our adding or subtracting these matrices, is the same as the two original matrices. Okay? So resultant is just a fancy word that just means the end result of a mathematical operation. So let's take a look at this one right here. Why not? Okay, this one has 2 rows and 3 columns. This one has 2 rows and 2 columns. So this is not possible. Can't do it. If they don't have the same dimensions, you cannot add or subtract them. Okay? So if we take a look at this one is a 2 by 3. This one is a 2 by 3. So the resultant would also be a 2 by 3. Everybody watch, please. The resultant is a 2 by 3. Now sometimes, granted on this one, it's pretty small. It's pretty easy to keep straight. Sometimes it's helpful to go through and just put little lines to say, hey, here's what I've got to do. I've got to fill in these 6 numbers. I've got to fill in the 3 numbers on the first row and the 3 numbers on the second row. So we'll go through here and we'll figure this out this way. Element by element. I'm going to take 1 and I'm going to subtract -6. 1 minus -6 would be 7. So that first row, first column entry is just going to be a 7. Next one, 2 minus 3. So that's going to be a -1. -3 minus -4, so that's going to be -3 plus 4, so that's going to be a +1. And you just go through element by element, position by position, add them, subtract them, whatever the case happens to be. So on this one right here, this is -8, right? And then we get -5, and then the last one 6 because we're just subtracting a 0, okay? Now, if you don't want to draw the little lines, that's okay. When we do matrix multiplication in a second, that can be kind of helpful. If you're really neat and organized, which some of you are and some of you are not, okay, Jared is ridiculously organized. He's already done this assignment and he fit it on a postage stamp. So it's really impressive how organized Jared
Are you
is.
serious?
No, I'm not
I
serious.
haven't seen his handwriting.
No.
Tiny.
Oh, you're
Okay.
grading his next paper.
Yeah,
Okay.
You're grading his next paper.
So we want to run through here. And we want to do some addition and subtraction. We do want to talk for just a second. Is matrix addition, would it be commutative? Could you change the order? Like, could I put this one first and that one second if it were addition and get the same answer?
Yeah.
Yes.
You can. What about subtraction?
No.
Just like regular addition, subtraction. Subtraction is not commutative. Okay. So let's look at this one right here. We're going to have a 2 by 2. Again, if you're nice and neat about this, you can keep these straight. Just keep in mind I've got to put 4 entries in here. So make sure you save enough space for them. Okay? Again, lined paper, putting little dots on it or something might be helpful. So this is going to be a -5. This is going to be a 2. This is going to be a 7. And that's going to be a 9. Looks nice and neat. There's the answer. You'll notice its dimensions are 2 by 2 as well. 2 by 2 on this one also. -5, 10, 5, and 3. Did I get that right?
Yeah.
Okay. Okay, notice the last one.
It's the same.
When you first of all, you can add the 2 of them together. They're both 2 by 2s. When I put those together, I've got 0 plus each one of these. So every one of these is a 0. I'm just adding each one of those elements. So I get 1, 2, 4, and 5. Okay, this is called the 0 matrix. Now, if I add the 0 matrix to another matrix, just like if I add 0 to another number, okay, 0 is called the additive identity. It's called the additive identity because when you add it, whatever you added it to maintains its identity. It stays the same. It doesn't change at all. Okay? All right, any questions there? Easy stuff, right? Okay, so we do need to be able to, we run into a difficulty when we start working with quantities that aren't necessarily plain old numbers. So we run into a problem like this. If I look at this example 5 right here, there's a 5 right here and there's a 5 right here. This one is not part of a matrix. It's just a plain old number. This one is an entry or an element in a matrix in some bigger scheme of things, okay? So those 2 5s are not the same. We want different names for those, okay? So if we're dealing with a plain old number, we call this a scalar. And we actually use the word scalar in more applications than just with matrices. So if you take trigonometry, scalars are going to come up again there. Okay, so that one's a scalar. This one right here is just an entry, or usually we call it an element. Okay? So we've got to have this way of distinguishing plain numbers from numbers that appear in a matrix. And the way we do that is we introduce a vocabulary word called a scalar. Scalar is just a plain old number. Okay? Now, scalar multiplication is really easy. Scalar multiplication works like distributing. We just multiply element by element. So if you flip the page over and look at example number 6, here are some examples of scalar multiplication. This is different than matrix multiplication that we're going to do in just a second, but it is very easy. Okay? It doesn't have anything to do with the dimensions. All we do is we take that 3 and essentially make all of the numbers 3 times bigger than they were. If it was a -3, we distribute a -3 to those. So the resultant on this one, again, that word again, it's just the end result of this mathematical operation. 3, 6, 12, and 15. There's our resultant matrix. Now, it's not uncommon to see something like this on a test or a final or something like that, just to see if you know what you're doing. Okay, very easy problem. This is a 2 by 3. The scalar that's sitting out front, or the scalar that we're going to distribute through, is a 5. This is a 2 by 3. The scalar that's sitting out is either you could think of it as a +3, and we're going to subtract it, or you could think of it as a scalar of -3 that we're going to distribute through and then combine the results. Yeah?
When you're distributing the 3, can you distribute it as a -3 and then turn it to a positive?
Sure, there are a couple different. I think this is the easiest way to do this. I think focusing on the negative and dealing with that all at one time, I think, is the easiest way to go. So let's go through here and just multiply all these by 5. So this is going to be 5, 10, -15, -5, -5, and 10. And then when I write this one down, I think the easiest way to get this correct is to go through and let's distribute the -3 through. Okay, because then we're just multiplying by a negative, which for some reason is easier than subtracting. Okay, so I'm going to put a plus here, and then I'll distribute that negative through. So I get a 9, a -9, and a 12. Down here I get a -3, a -24, and a 0. And then I'm just going to go through and I'm going to combine those. Again, I had two 2 by 3s to begin with. I'm going to end up with a 2 by 3 when I'm done. So I end up with a 14, a 1, a -3, a -8, a -29, and a 10. Okay, did I do the arithmetic right?
Yes.
Okay, this is not very difficult to do. Again, what might bog people down is just the sheer number of calculations. We just did, in order to get that right, we did somewhere in the neighborhood of 20 calculations. Right, but if you screw one of them up, you get the answer wrong, okay? So just like with row operations, with augmented matrices, the process isn't very difficult, but if you make a silly mistake, you're going to get the answer wrong. Let's just double check this because you can do this one more way. Let's say I take this, 1 times 5, that's a 5, and then -3 times -3, that's a 9. 5 and 9, 14. I could go through, not have to rewrite anything, but again, I'd have to keep track of all of those little arithmetic problems, and I'd have to make sure I did every one of them correct in my head if I'm not going to write anything down, okay? So make sure you're careful with that. Okay, so all of those are pretty easy. This is slightly more difficult, but once you get the hang of it, it's not very bad. Yeah?
So that's just it. That's the whole answer of what we get.
This right here is the whole answer. Yep.
Okay.
End of story. Any questions? Yeah. That is a good question, and no, they're not. Do you need to run to the restroom? Okay. All right. So let's talk about matrix multiplication. Matrix multiplication is a little bit more complicated. The dimensions of the matrix have a large role to play, and it seems a little bit weird the way this works out, but this is how we multiply these together. Okay. So here's what we've got to check. The number of, let's see, columns in the first matrix must be the same as the number of rows in the second matrix. That's the first thing we have to check. The next thing we have to check is the resultant will have the same number of rows as the first matrix and the same number of columns as the second matrix. Okay. And then we're going to use something that I call the karate chop method. It works better when I was teaching on a whiteboard because you could actually see where my hand was, but maybe I'll draw it up there if we need to. Okay. So here's the idea. Again, the first thing we have to check is, do the dimensions make it so that we can multiply these together? This is a 2 by 2. This is a 2 by 1.
No.
Okay, thank you for the outburst. Okay, we can multiply these together. Another way to describe the fact that the number of columns in the first matrix has to equal the number of rows in the second matrix is this. The inner dimensions, these guys right here, have to be the same. Are they the same? Yes, they are. Okay, then let's figure out what are the dimensions of the resultant. When I multiply these together, I end up with the same number of rows as the first matrix and the same number of columns as the second matrix. So I'm going to end up with a 2 by 1. So again, the first thing you want to do is write down the dimensions of each matrix, make sure the inner dimensions are the same like this, and then figure out the dimensions of the resultant. So the resultant is going to be a 2 by 1. 2 rows, 1 column. I only have 2 numbers that I need to find here, and I'll have this buttoned up. Any questions?
Yeah, how do we find this?
I'm going to show you. Thank you for asking. Okay, so here's the karate chop method. What I would normally do when I'm doing this is I'd say we're going to karate chop the first row with the first column. Okay, so I would look at it and say this. What position is this? First row, first column, right? So I'm going to take the first row, this one right here, and karate chop it with this one right here. They're going to kind of multiply correspondingly. So when I take this row and multiply it by this column, I multiply the 1 and the 1 together, and I multiply the 4 and the negative 2 together. So I get 1 and I get negative 8. Guess what I do with those? I add them together. I just combine them together. So I end up with negative 7. Okay, where is this entry in the resultant? Where is this answer? Second row, first column. So I take the second row and karate chop it with the first column. So again, you're going to take this one right here, take that row, karate chop it with that column. See how the 3 and the 1 would correspond? And the 0 and the negative 2 would correspond?
How do you know that?
How do you know what?
Which one corresponds with which one?
Well, okay, that's what I was asking. Okay, let me show it again. If you take this row and karate chop it with this column, okay, see where the tip of my fingers are? See how they're by the 3? If I karate chop it with this one, the 3 would go with the 1, and the 0 would go with the negative 2. Is that all right? They just go kind of right in corresponding order. Yeah, and if you'd make thumping sounds when you karate chop on the test, yeah, that's fine. Yeah, okay.
I will, don't worry.
Okay, so I'm going to multiply the negative 3 and the 1 together. Then I'm going to multiply the 0 and the negative 2 together. I get a negative 3 and a 0. What do I do with those?
Add them together.
Combine them together, and what do I get? I get a negative 3. Okay, and that's it. That's the answer. Okay? Okay, now I find it useful to actually write this out this way, to draw the 2 by 2, to put the dimensions underneath it, to put the little lines so I know how many I'm looking for. So I'm going to do the same thing on this one. Is everybody ready for B?
Yes.
Okay, this is a 2 by 2. This is a 2 by 3. Can I multiply them? Are the inner dimensions the same?
Yes.
They are. These are the same. What are the dimensions of the resultant?
2 by 3.
Has the same number of rows. It's got the dimensions we left out, right? Start with the 2, end with the 3. So here's what we've got. I've got these 6 entries that I need to fill in. Okay? Any questions? Okay. Everybody watch, please. I want to make sure you get it right. I'll turn you loose in a second. Okay. Where is this entry? Where is this element? 1, 1. In other words, it's in the first row, first column. So I take the first row here and I multiply it by the first column there. And notice what corresponds. The 2 and the 1 correspond, the 4 and the 0 correspond. So I've got a 2 and a 0. So what entry do I have here?
I have a question.
Yes.
What if you did the other way? Would it make a difference?
It would make a huge difference. We're going to talk about whether or not it's commutative in just a second. Okay, is everybody okay with that? Okay, again, where is this one? It's still in the first row, but now it's the second column. So I'm going to take the first row and multiply it by the second column. So the 2 and the -1 correspond, the 4 and the 2 correspond, so I've got a -2 plus an 8. So what number do I put there? I put a 6 there. You with me? Okay, ask a question now, because it's just, once you get the method, it's just, can you do the little arithmetic problems fast enough? Okay, where is this one? First row, third column. So let's take the first row and let's karate chop it with the third column. So the 2 and the 0, the 4 and the 5. And what do I put here? I put a 20 there. Okay. Got it? Where is this one? Don't say anything out loud. Where is this one? Get it in your head. It is in the second row, first column. So that means I'm going to take the second row and karate chop it with the first column. So which ones correspond? The 1 and the 1, the 1 and the 0. So I multiply those together and I get a 1. Where is this one right here? It's in the second row, second column. So I'm going to take the second row here and karate chop it with the second column. So 1 times -1, that's a -1. 1 times 2, that's a 2. -1 plus 2, I get a +1. Last one, think to yourself, where is it? Where is this entry that I'm trying to figure out? It's in the second row, third column. So I'm going to take the second row of this one and karate chop it with the third column. So 1 and 0, 1 and 5, I end up with a 5. Okay, are there any questions? Do you get that? Okay, let's take a look at this one. What is this? 2 by 1. First thing you have to do, you can't multiply them if the inner dimensions don't match up. This one is 2 by 2. You have homework problems like this. Don't sit there and go, well, let's see, I need to multiply the 1 and the 1, the -2 and the 0. If the dimensions don't match up, you can't multiply.
Yeah.
She says with glee. Okay, there is no solution to that. Okay, can't be done. Any questions there? Okay, this looks a little bit weird. Can you do this?
Yes.
Okay, this is a 2 by 3. It's being multiplied with a 3 by 3. The inner dimensions are the same, so we will get a resultant. The resultant will be a 2 by 3. Now, for a lot of people, they'll look at that and they'll say, that's just weird. How can you multiply a 2 by 3 with a 3 by 3 and still end up with a 2 by 3? Seems strange. Okay, but let's take a look as to why this is, why the dimensions have to match up this way. Okay, this one is in the first row, first column. So I'm going to take the first row and multiply it with the first column. Notice how everything matches up. This is why the inner dimensions have to be the same. If I have 3 columns here, I've got 3 numbers in the first row, I better have 3 numbers here in this first column to have them match up. Okay? So 3 with the 1, -1 with the 0, 1 with the 0. What's my answer?
3.
You do the next one. First row, second column. First row, second column. Karate chop the first row with the second column. What do you get? -1. First row, third column. First row, third column. First row karate chopped with the third column. You get a 0, 0, and a 1. Okay, do you notice anything? Let's do this one. Hopefully you see a pattern here. Where is this? Second row, first column. Second row, karate chopped with the first column, so 0, 0, and 0. Does anybody notice anything?
Yeah, it's just going to be negative 2, 5.
This one's going to be negative 2, and this one's going to be 5. You with me? Okay. What do you notice? What's that?
It's like multiplying by 1.
This thing right here is like multiplying by a 1. It didn't change it at all. Okay, that's called a multiplicative identity. Okay, and it's called an identity matrix. Okay, so we'll talk about that again in just a second. I want to make 2 other points. This is a little bit unique. 2 by 1, 1 by 2. Weird. What do you get? You get a 2 by 2. First row, first column, negative 9. First row, second column, 12. Second row, first column, negative 6. Second row, second column, 8. Right? Pretty cool. Okay, so is matrix multiplication commutative? Could you move them around? Let's take this one and switch the order. It would be a 3 by 3 multiplied by a 2 by 3. Are the inner dimensions the same? Okay, it is not commutative. Okay, matrix multiplication is not commutative. Okay, this matrix right here is what we call the 3 by 3 identity. Okay, so when we multiplied that matrix up here, it acted like a 1 when we multiplied. Okay, again, that's called an identity matrix. Identity matrix. It's actually the multiplicative identity if we got really technical about the name, but we typically just call it an identity matrix. It acts like a 1. So the notation that we use for this, and you will see this occasionally, if I write I sub 2, it means the 2 by 2 identity. So 1's down the diagonal, 0 everywhere else. So that kind of row echelon form type idea, okay, comes up again. That's not an augmented matrix. Okay, it's a square matrix in this case, but it's 1's down the diagonal, 0 everywhere else. This would be I3. This would be the 3 by 3 identity. That's what we multiplied by here. So if somebody said I4, what would that be?
4, 1.
Okay. So it'd be 1's down the diagonal, 0's everywhere else. Okay, that would be I4. Okay, what about I1?
Just a 1.
Just a 1 in brackets. Okay, a 1 by 1 matrix. Okay, any questions? Okay, haven't said anything about division yet, and there's a good reason for it. We usually don't divide by matrices. We get a little bit tricky about this. We already know how to do matrix multiplication. Okay, and multiplying matrices really isn't that bad. You just check the inner dimensions. Okay, and then you go karate chop method, row by row and column by column. Okay, so if I gave you this equation right here, 5x equals 30, and I said you can solve that, but you got to solve it without using division.
Exponents. Use fractions.
I suppose you could use exponents, fractions, multiply by 1/5. Okay, what we're going to do here is we're going to multiply by, it's called the multiplicative identity. Multiplicative inverse. Multiplicative inverse, okay, is what we're after here. So the multiplicative inverse of 5 is 1/5. It's the reciprocal of 5. So what that does is it cancels it off. It's the inverse of multiplying by 5. Okay? Multiplicative inverse. So I get an x over here. I do a little bit of canceling here, cross cancellation, and I end up with a 6. Okay? So I can solve an equation that has multiplication in it, that I don't need to use division. I use the multiplicative inverse. Okay? All right. So what we're going to do is we're going to multiply by the inverse of a matrix. And it can be a really good way of solving a system of equations, but first we need what's called a matrix equation. So we just solved this simple little equation right here. And my contention is if you know how to solve that, we're going to use the exact same structure to solve what we call a matrix equation. Okay? So a matrix equation consists of a coefficient matrix, a variable matrix, and an answer matrix. So coefficient matrix, that shouldn't sound too unfamiliar. We've actually talked about that before in 8.2. An answer matrix, we called it an answer column matrix before, but that shouldn't be unfamiliar. And then we're going to have a variable matrix. So let me show you this. I'm going to take this and I'm going to write down the coefficient matrix. Now, the coefficient matrix, I think everybody ought to be able to get that. We've got a 1, a 1, a 1, and a negative 1, right? That's the coefficient matrix. Okay, I'm going to write equals, and then on the other side, I'm going to put the answer matrix. It happens to be a column matrix because there's just an 8 and a 4 stacked on top of each other. So that's an 8 and a 4. Now, this is a 2 by 2. This is a 2 by 1. And I'm going to multiply this matrix here by something, and it's going to produce a 2 by 1. Now, if I multiply it by something, first of all, it's got to start with a 2, right? It's got to have 2 rows. How many columns would it have? It would have 1. Because remember, these inner ones are going to be the same. The outer dimensions are the same as what we get for the dimensions of our resultant. So what I've got right here is a column matrix. It has 2 rows and 1 column. Now, if 1, 1 and 1, negative 1 represent the coefficients, and 8, 4 represent the answer column, what do you suppose goes in here if we're going to write this down as an equation, as a variable? X and Y. Just stack them on top of each other. Okay? This right here is what we call a matrix equation. Okay? So that is a matrix equation. And the point we want to make is, although this looks kind of ugly, it does have a nice little format. Notice what we've got here is a bunch of numbers times a variable equals another set of numbers. A lot like what we had up above, 5 times x equals 30, and that was a very easy equation to solve. Well, this is going to be not quite that easy, but we're going to solve it in roughly the same way. Now, let's just double check and make sure that this actually is true, that I've represented this accurately. If I multiply a 2 by 2 with a 2 by 1, I get a 2 by 1, right? And let's see, I need an entry here and an entry here. Where is this entry right here? 1, 1. Okay? First row, first column. So if I take the first row and multiply it by the first column, 1 corresponds with x, 1 corresponds with y. I multiply the 1 and the x, the 1 and the y, and then what do I do to those? Add them together. So what's 1x plus 1y? X plus y. Okay, where's this one? Second row, first column. So I'm going to take the second row and multiply it by the first column. So the 1 and the x, the negative 1 and the y. So that's an x and a negative y. Put those together. This says x minus y. Now, it equals this 2 by 1 over here. And what did it equal? 8 here and 4 there. Now, remember on the previous page when we talked about equality? What's the only way these two matrices can be equal? If they have the same dimensions. Do they have the same dimensions? Yes. And they have to be equal element by element. So is this one equal to that one? Is x plus y equal to 8? Yes. Is x minus y equal to 4? Yes. That represents our original equation. Okay, are there any questions there?
That's the answer?
That's how we'd write it down as a matrix equation. Okay. Now we're going to solve this. Okay, are there any questions there? All right. So once we have our matrix equation, once we have it looking like this right here, then we can solve this using an inverse operation. Okay, an inverse matrix, a multiplicative inverse. It's like the same as multiplying by 1/5 on the previous page. So we need to find the inverse of the matrix of coefficients. If I can find the inverse of that right there, I could multiply both sides by it, and it would undo multiplying by that original inverse. So if A is a matrix, then this is the notation we use. That's not an exponent, okay? It just means we're going to do the inverse of that. And here's how we find the inverse. Okay, the inverse of a matrix is 1 over the determinant. We'll put a comma there. So you have to find the determinant, and you do 1 over the determinant times the transpose of the matrix of cofactors. So transpose is a new word, and matrix of cofactors, we've heard of cofactors before, right? Okay. So let's go through and let's find some inverses. 1 over the determinant times the transpose of the matrix of cofactors. So we know what cofactors are. Let's talk about what a transpose is. A transpose is a right-hand pancake flip.
What?
You can, if you can spell spatula, you can put that there too. I'll show you what that means. Okay, first thing we want to find is, what is the determinant? Now, determinants of 2 by 2s are pretty darn easy. So this is going to be -6 down the diagonal, write the minus, and then go up the diagonal. That's a -8, right? So what do I get? +8. So this is going to be a +2. So it's 1 over 2. Okay, now I'm going to put a little t up there to remind us I need to find the transpose of this. But I'm going to write down the cofactor for each one of these. So I need a cofactor for every one here. Okay, remember, a cofactor is the sign associated with the position times the little determinant that's left if we cross out the row and the column. So look at this right here. What is the sign associated with this position? Okay, sign. Positive. Okay? Now, if I cross out the row and the column, what's its minor that I have to put there? A 1. So the cofactor is +1. Everybody with me there? Okay, what's the sign associated with this position? Negative. Cross out the row and the column. What's its minor? -2. So it's a -2, so that's a +2. Sign associated with this position? Negative. What's the number that I put there? A 4, because that's its minor. And what's the sign associated with this position? Positive. And what's the number that I put there once I cross out the row and the column? -6. Okay, so to clean this up, here's what I've got. I've got 1/2, a 1, a 2, a -4, and a -6. Am I right? Okay. Now, I still need to transpose that. Now, when I say transpose, again, I haven't taught this class for a couple of years, so it's a little harder on a tablet. When I say right-hand pancake flip, what I mean is, if you were standing right here and you slid your right hand underneath this and just took it and flipped it over. Okay, think of flipping a pancake. What happens to these two numbers here? No, take your right hand, slide it underneath there, and go like that. The 1 and the -6 stay exactly where they are. What happened to the two of these? Okay, so whatever's in this upper quadrant here flips with this lower quadrant right there. So this is 1 over 2, and then the 1 and the -6 stay in the same place, and this is a -4 and a +2. Now, everybody listen. If you don't have a calculator, it's actually better if you leave it like that. Because if you have to use it again, it's easier to have whole numbers in there. Okay? Now, if all they say is just find the inverse, here's what the inverse would be. The inverse would be 1/2, -2, 1, and -3. That right there would be the inverse. So this is useful, but this one right here would be the inverse. Everybody with me? branch of, where did this come from?
Where did that come from?
We just did scalar multiplication. We just distributed to 1/2 through. Everybody okay with that? Okay, let's do one more. Okay, the first thing I need is, I'm going to change colors. The first thing I need is the determinant. Negative 35 minus, write the minus, and then this is going to be minus 30. So the determinant is negative 5. So we're going to do 1 over negative 5, and then the transpose of the matrix of cofactors. So I'm going to find the cofactors to start with. Sign's positive, what number do I put there? Negative 5. I'm going to put a negative in front of whatever the minor is. What is it? Okay, so this is going to be a negative 5. Everybody okay? Sign associated with this is negative, so whatever I put there, I'm going to change its sign. What do I put there? A negative 6, so negative, negative 6, that's going to be a 6. And this one right here, sign associated with that position is positive, so whatever I put there, I'm just going to leave the sign alone, and it's going to be a 7. Now, this is, if you had to use it again, this wouldn't be too bad. You could also do this. This would be, so if I distribute the negative through, this would be 5, 5, negative 6, and negative 7. That would be okay. Either of those would be pretty good to use again. But what if they said, hey, I actually want you to, oops, you're right. I didn't do the transpose, did I? You're right. So let's transpose that. Right-hand pancake flip. So I've got this. The 5 and the 7, the negative 5 and that 7 are going to stay in the same place. And these guys are going to switch places. So that's going to be a negative 5 and a 6. Okay, there. That you could use, right? If you distribute the negative through, we could have a 1/5 sitting out front, and then a 5, a negative 6, a 5, and a negative 7. That would be okay. Either one of those would be okay to use again if you had to. If they said, tell me what the inverse is, you'd want to distribute that through. So that's going to be 1, negative 6/5, 1, and negative 7/5. So if somebody said, hey, tell me what the inverse is, this is the one that you'd want to tell them. That's what you'd want to give them. Okay? All right. Any questions? You sure? Yeah. Because the determinant, this is negative 35, and then it's minus 30, so that would be plus 30, so that's going to give us negative 5. Got it? These are all the cofactors. This is what we get when we do a transpose, a right-hand pancake flip, and then I just distributed the negative through to get this, and distributed the 1/5 through to get this. You can just distribute the negative through, and these two would turn into positives 1s. These would turn into negative 6/5 and negative 7/5 respectively. Good there? Okay. You will be asked to find the determinant, the inverse of a 2x2 by hand, and you'll be asked to find the inverse of a 3x3 by hand. If you'd like to look at how the textbook says to do it, be my guest. They actually have you do row operations. They have you do this. Everybody listen. They have you write down the original matrix. They have you augment it with the identity matrix, and then they have you put this one in reduced row echelon form. So each row has like 4 elements in it, or it has 6 elements in it if it's a 3x3. So you have to do a bunch of row operations. It is hundreds of calculations usually, okay? And screw one of them up, you get it wrong. This is a heck of a lot easier, okay? You have to know how to do this 1 over the determinant times the transpose of the matrix of cofactors to find a 3 by 3. Would you like to see an easy way to do a 2 by 2? Okay, so here's how it works. You still have to find the determinant though. Okay, so let's find the determinant here. This is going to be, well, let's see, wait, this is good. -7 minus, oh no, not so good, -13, right? Okay. Let's see, did you notice anything about, let's see, let's take a look at those two right here. There used to be a -6 here, and now it's down here. And there used to be a 1 here, and now it's up there. And that 2 used to be negative, and that 4 used to be positive. Okay, so here's what we do. You still have to find the determinant. So this is 1 over -13. Okay, these two switch places. Literally just switch places. So there's a 7 here and a -1 here. These two change signs. Not switch signs, they change signs. So if this was a +2, that's a -2. If this was a +3, that's now a -3.
But they switch too, don't
They don't switch places.
they? They did it.
No, take a good look. Here's the original one. Here's the answer. Look how the 4's in the same place. It just changed signs. Here's the 2. There's a 2. All it did was change signs. So the upward diagonal, they get to stay where they were. The other diagonal, they switch. But again, on that upward diagonal, they have to change signs. So the answer to this one would be -7/13, +2/13, 3/13, and 1/13. That would be the answer. Again, there wouldn't be anything wrong with using this to solve another problem or something like that, but that's what we'd get there. Okay, so let's just write down a quick formula for this. This would be 1 over A times D, whoops, write a D, minus B times C. Okay, what happens to the downward diagonal? They switch places, so that's going to be a D here and an A here. What happens to the upward diagonal? They change signs. Okay, they switch signs, so that's going to be a -B. What?
D's gonna, can you give me the inverse of 0? Because 4 times -2 is a -8.
Which one are you on?
D.
Okay.
You get 0 as a determinant, which means it's going to be 0.
Oh, so I need to catch that. Let me make that one an E next time. So this is -8 minus -8 plus 8. So that means the determinant is 0. Okay, if the determinant is 0, what does that mean about our little formula here?
It doesn't work.
You get 1 over 0, and this is undefined. We love those because then there's no inverse. Okay? All right, we're going to stop there. You have enough information to get started on 3.3. You can do most of it. The only thing you won't be able to do at this point is finish solving a matrix equation and find the inverse of a 3 by 3. We'll pick up there tomorrow. Thanks.